All right, so let's finish our introduction. I have silently uploaded the lecture file, the PDF, on Canvas without saying a peep. Normally, I will actually send an announcement that I posted it, but it also might just show up if I get too busy. So it's in a lectures folder in your Canvas, so you will find a PDF of these slides. But let's basically get back to what we started with last time. I mentioned that we have science and engineering. Both need each other. We are engineers, but we need fundamental knowledge that science provides. And basically, the task of an engineer is to figure out how do fundamental laws play in whatever situations they have, which one is the most dominant, so what do you need to model first, especially if you have to do a quick calculation. And then from then on, sometimes you have to do trial and error to actually figure out how something works. And tools you use in building any knowledge, whether it's science or engineering, are basically theory, experiments, and computation. And they're kind of shown in these figures here. And the computation part is the most recent tool. I'm not gonna, well, actually, I can play a movie. Here's a Dr. Oden explaining computation that basically flourished since Second World War, give or take, with the invention of computers. Dr. Oden is from UT. Just gonna play it.
So what happened toward the middle of the 20th century, and particularly in the last 25 years, was the advent of scientific computation. People learned how to take theories and turn them into mathematical languages which could be put on a computer, could be discretized and processed by a digital computer. The computer made possible a huge extrapolation of man's ability to use theory and to use observation.
This is how he became.
I would say my biggest
I'll let it play.
model was my father and my grandfather. We were a close family. They spent a lot of time with their kids. They taught us the value of education. And I guess my younger life, I wanted to be as much like them as possible. I really enjoy working with students. It's invigorating. It's energizing. I have to explain things to students and I find out what I don't know. So you have to put things in words in a way that you think you're conveying information. And you realize, well, maybe I better patch up some things I thought I knew. So the thrill of learning something new is why people go to a university and why they stay there.
There you go. So you met Dr. Oden in 2 minutes and got the basic idea of what is computational engineering about. Now, just a bit of history to put a couple of numbers on what he said. Today, we wear computers. Okay? Your Apple watches are computers. These days, there's like you can have those Google glasses and whatnot. They have a small computer with them. So we don't even tend to notice how prevalent computers are in our lives. But if you actually want to look how computers looked like early on, 1940s to 1950s, they were filling up a room. People here are for scale. Okay? So essentially, one computer was one room. And on this, if you follow this link in the slides, you can see some of the earliest computers and their photos. And very recent movie, Hidden Figures, it's in the theaters right now, and I'm going to go back to it in a moment. It actually shows NASA Space Center installing its first computer in 1961. In 1963, there were 15 only computers. Probably each of you owns 3 in some shape or form. Okay. In the entire state of California, in 1973, there was 1 central computer at the University of Texas at Austin, a premier research university. Okay? So just things were developing fast at that time in terms of computer. Today, we just take them for granted. Now, I highly suggest viewing Hidden Figures for a historical perspective. It's a historical perspective on all, it's a layered movie. Okay? It has a lot of points that you can get from it. It has a space race, basically United States versus Russia at the time, as a main motivator, and that was motivator for developing a lot of technology. At the same time, movie is dealing with the issues, societal issues, such as race, and the fact that race and being a woman, and the fact that at that time, there was none of those really in computing, and computing in itself, or engineering, was in development. So it follows 3 main protagonists, but basically what everybody, I enjoyed the movie, it's great storytelling as well, and it kind of tells a story that hasn't been really present in the mainstream, but you can find some timeless lessons in there that you as a person can, as an engineer, can take in overcoming adversity, whatever shape of that adversity is, and that basically with perseverance and hard work and vision, where you're going, you can overcome those. Whatever it is that comes your way. And that time, space race is something big, it's on TVs. Petroleum engineering is not so much on TV, but you're equally, constantly at the edge of technology and frontiers are moving. And at that time, it's always important to recognize where is something going and try to get there sooner, because that keeps you basically moving, that keeps you employed. So it's actually some timeless lessons for everybody in there. One moment that I like the most is that one of the characters, Dorothy Vaughan, she's a supervisor of a human computing group. So there were human calculators before computers that calculated things by hand. Okay? That was the job of mathematicians and engineers at the time. And she's the head of that group. And she sees this IBM first computer being installed. And it's this big thing coming in, right? Nobody really knows what it does, how it does it, right? And she figures it out, starts playing around it, comes in the evenings to basically play with the machine and program it, and realizes, oh wow, this thing does 24,000 operations in a second. That's way speedier than a human. That's going to replace that human. So what about people who are doing those calculations now? She goes to the library, she finds a book on Fortran, which is a programming language, learns how to do it, and teaches her group how to do it. That's vision. That's a leader. Okay? So you also have to, you will be at the edge. It's frontier. Your textbook, I can't tell you what's going to happen in 10 years, but you will be there. Okay? So you have to recognize that moment, and then no matter what, try to jump ahead. Okay? And preempt, because you will basically, and she actually saved the jobs of those 20 women in that group. Add social context to it, there's also 10 black women who would have lost jobs first in any situation. That was the reality. Okay? So be that leader. Preempt. Okay? So that's something, those are some timeless messages that you as an engineer, you're constantly going to be reading. Okay? I did mention how deeper and deeper we're going, okay, in terms of drilling. So there's constantly something that we don't know and we didn't do before. Okay? So you have to fight both the physical forces, the engineering forces, and those that are political. Is whatever it is that you want to do, is it going to be approved? Okay? You have to fight with various society, like saying, no, you can't do that. Right? How are you going to convince somebody that you should be going there and that you know what you're doing? Okay? So there's a lot of lessons that you can learn, and just think about it as you go, because you will be at the frontier. Okay? And second thing is also there's, as the movie progresses, they start using that computer for calculation, for sending to the person to the, I should maybe be revealing all of the plot, but basically, computer did a mistake. And you will learn about errors as we go through. So the computer also had to be tested. And then they ultimately invited one of those human calculators to come in and save the day, okay, as they sent the first person out there to the outer space. Okay? So, and she did. So also, do not trust technology blindly ever, however mighty it is. Computers only do what you or some other human told them to do, and that's not without mistakes. So they do certain mistakes that we can predict, but there are also unpredictable ones. So again, you always have to be at the edge of your seat and preventing those. So again, lots of messages, but it's also beautiful historical context of what you take today for granted versus what wasn't there before. Okay? My joke is that we have these computers in our pockets these days, which are phones, that basically are much more or much stronger and better than the computers that sent Apollo 13 to its mission. Okay? Yet what do you do with it? You go on Facebook, like pictures of cats. So it's kind of, it's funny how that works. But we could actually have this powerful machine. Now, to continue a little bit with the history, equivalent of today programs, or we will encounter M scripts in MATLAB, is the data entry. So you have to somehow feed the computer with data. Okay? And initially, well into 1970s, what you fed the data, the way you fed the data into your computer was a bunch of punched cards, literally pieces of paper. Okay? So basically, we would stack that punch card business into the computer, give it to it, read it, do its thing, and spit out, print out the result. So I'm going to actually let Dr. Bomer, this was actually an assignment in this class, to record two professors that have experience with punch cards. Okay? So you can count your blessings for not being required to use them. I'm not joking. Let me just quickly go.
When did you use punch cards, and what was it with industry? Was it with like schooling, and then what did you use them for?
When I learned how to program at the University of Texas from about 1973 to 1979, punch cards were how you did it. Punch cards were the way you communicated your program to the computer. And they had some typewriters basically, and you would put your cards in and they would be sucked into the typewriter, and then whatever line of code, one line only, one line of code you typed in, and then it would punch a hole at strategic places across the card. So if I had a program that was going to have 10 lines of code, I would have the first card would be, they called that the job card. That's how the computer knew new job. Mm-hmm. Then after that came the cards that were line by line by line by line of the program. Then there would be an end card, and then if you had any data, that came next in the format that the program told the computer to expect the data. And then last but not least, as I recall, there was a green card that was the end, termination of job. So everything between the start card, the job card, and the termination green card, that was your program and your input data.
Oh, wow.
So if you weren't good at typing, this would take a long time. And so let's say I've got my little program deck and I take it over to the computation center at the University of Texas, and they had some card readers. So they had big trays, and your program would go at the end of the tray, and they would take that one, put it in, read every card, put that deck back in the output, and then you would wait. So the computer now is thinking about getting to my program, and it finally spits out a hard copy. And it would show the listing of the program. It would show results, if it got to the results. If it thought there was a programming error, it would put a code down at the bottom. You need to look at this line. There's something here I don't understand. So then you'd have to go figure out what was wrong, retype the card, resubmit the job, all over.
How long would if you just wanted to do one normal job, how long do you think that would have taken?
Well, it depends on how many people are using the computer at that moment, because in those days, the University of Texas had one central computer. Every place on campus fed their programs to that machine. To make a long story short, if your program was really a small program, well, you could probably get that back in an hour. But if it was a big one, or if there were a lot of people using the machine, if you got 2 runs per day, you were probably pretty happy.
Wow. Do you ever miss punch cards?
No.
Were they phased out because of the computers and like the processing power and all of that?
No doubt, no doubt. Processing power and the storage capacity of computers started getting to the point where I could take my program and I could sit here at my terminal and I could type in my program electronically and I could save it as an electronic file. And then whenever I was ready to submit it to the computer, I could. So as the data storage capabilities got better and better and better, nobody really wanted to do punch cards. It was the only way you could get your program recognized by the computer. But in 1973, trust me, that was whiz-bang stuff. That was the cutting edge. That was the way everybody did.
So, remember this when you start complaining about debugging your programs later this semester. Just put it in perspective.
How punched card programs work.
Whoa, whoa, whoa. Hi.
University of West.
That's okay. you got the basics. So just remember this down the line when you want to punch your own computer or spitting out some weird results, but you're sitting in your room, as opposed to remember Tuesday how much it was raining. So let's say you typed everything correctly into that stack of cards and then you walked outside in the rain and you didn't bring your umbrella. Well, you wouldn't be able to take that deck of cards to the computing center, would you? Right? And everything that we do, we'll do it on computers, but you can do it on your smartphone. The small screen and all, but you can't. Whatever we do, you can do on your smartphone. Okay? So count your blessings and let's move on. Alright. So again, just to repeat, science and engineering objectives are typically different than in engineering. We have to do more applied problems, typically also bigger problems, whereas in science we do smaller and isolate much smaller systems to come up with fundamental laws. And because of that, computation is actually relatively more important in engineering because you can tackle bigger problems easier using computers, but be forward knowledge with theory, experiments, and computation. I'm of course emphasizing computation in this course, but whoever tells you that only one of those is most important is wrong. Okay? You need all three. Period. Okay? And all three, they look at the different aspects of the same problem and typically complement each other. Here and there verify each other, but most often complement each other, so we do need all three. Now, what is a numerical method? We sprinkled that word quite a bit. Basically, you learned in your classes so far, such as calculus, a differential equation, problems that can be solved analytically. That is, you can come up with a formula or a function that basically solves whatever equation you have at hand. Numerical methods ditch that and go and solve the problem computationally. The way that works is I typically what's called discretize my domain and take my physical space where I'm modeling things and I break it up in small numerical cells. And all I find is the value of that function at each cell. So if you're thinking about your computer and its screen, it has pixels. So basically, the result of a computational or numerical method is the value of the function you're after at every pixel. Okay? More pixels that you have for a given domain, the better. You have a finer result, but it can also be very coarse. So that is called computation. Most of the problems, so basically very small class of simple problems can be done analytically. Any real reservoir in petroleum engineering is a complex beast. It looks difficult because it is. It's very what's called heterogeneous. It has all of the different parts to it. There's no way you have an analytical result. So for those, you have to tackle them. So basically, real-world problems, you will often have to design numerical methods. Further, what's one of the main advantages of computation is that you can click that button multiple times. So yes, there will be some pain in designing a program and working it out to be correct, okay, and verifying it. But once you do that, you just kind of change the numbers that you feed to it and you recompute again and change the numbers, recompute, change the numbers, recompute, okay? And that's what you want. Because in a reservoir, you're not interested in one thing. You want to design what is going to be the best method. Therefore, you have to play out 100 scenarios, okay? And out of those scenarios, pick the one that works the best. That's how you optimize what are you going to do in the reservoir, right? So essentially, this repeatability is very, very important, and that's what computation allows you to do. You can repeat things experimentally as well. It's just there's more physical components and more physical moving parts, so it's a little more complex than just pressing a button. All right. So one of the numerous jokes actually exemplifies that. So it goes like that. 3 women, a physicist, engineer, and a computer scientist, basically theory, experiments, and computation, are traveling in a car, and suddenly the car starts to smoke and stops. And then each of them tries to solve a problem, and they have different ways to do that. Physicist goes sort of theoretically and says, this is a classical problem of torque. It has been overloaded beyond the elasticity limit of the axis, so of course the axis broke, and that's it. We evaluated what happened. We stopped there. Okay? Engineer says, oh, come on. This is some spark in a connecting rod. I should just go in with a hammer and fix the thing. Okay? And computer scientist says, what if you get out, wait a minute, and just go restart the whole thing? So basically, repeatability is the key of computation. So you can do things or repeat things a little more comfortably than you can in theory or practice. All right, so let's actually exemplify and have an example method. And we are going to implement right now in class an algorithm to sum up all numbers in a table. And we will imagine that this class is a table. Okay? Now, everybody think of a number and write it down. And let's go simple, between 0 and 5, so we don't have a lot of errors in computing. Okay. Are you done? Now, in each row, and we're not very well balanced, which is actually realistic, so in each row, the starting person will report their number to the person to their right. So if you're sitting like this, go to the right and report your number. And we will start from the that end, okay? And the person that gets the number will sum up the two and pass on the sum. Okay? So you guys will be done really quickly. Okay? I'll take a little longer in this row. So let's get going. So start, record your number, sum up. And the person at the end, please recall. Yeah. So the person here at the edge, write down the sum. Write down the sum. Just row. Yeah, you all deal with your row. Okay. Now everybody starting from up, you will tell your sum to you, sum it up, give to him, and so forth, and you will know the final result. Human calculators. Huh? Our overall total is 51. Okay? So we have designed the algorithm. Okay? 57. So we are debugging as we go.
Okay, 61.
61 is the final result. There you go. So do we see that people can compute, but there are some human errors involved. Okay? We also had here what's called a load balancing problem. They were done really quickly, and they were waiting for all of these long rows to be finished because we had only 2 people in the front row. Okay, they were done really quickly, and then they were sitting idle. Like, what are they all doing computing? Okay. This is actually a problem in so-called parallel computing, where you are employing multiple computers to work at the same time. Essentially, you break up the problem in small parts. You let each of you do one part and communicate the results to your neighbors. And that's how you proceed. And if one cluster of your computer has to wait for the other to finish, that's imbalanced load, and that can create problems. Okay? So that's essentially parallel computing. Again, parallel computing, these days, computers that fill up rooms are parallel computers. They're literally stacks of CPUs in cabinets, and those cabinets have to have some additional air conditioning and cooling, and of course that extra electricity coming in. But they're not necessarily out of reach. Most of the time when you're buying computers these days, you're buying a dual core or quad core, meaning that there's quad core, 4 cores inside your computer. They have some of the memory common, but basically they enable you that one core opens Word, the other one opens MATLAB, third one opens your browser, and so forth, so they can be faster doing things in parallel. Same concepts are done in especially reservoir simulation. We will not get to the parallel computer. I just wanted to basically give you what is the edge today. Okay, we will continue on Monday.